All right. Let me go ahead. I'm going to put in the information from OneNote here. And somebody asked me about a different problem. But y'all see what I've got here on the screen? It looks like a WYSIWYG. What you see is what you get type of layout, everybody. So for this problem, the last problem, I like to work a couple of problems each. It says it's infinitely long. The frequency is 100 megahertz. So 100 megahertz is going to be 10 to the 8th, right? And R is, so now I've got to put these parameters in. We get rid of this stuff. I've got R is equal to 0.001. Then we have L is equal to 10 to the minus 6. C is equal to 2 picofarads, 2 times. Oh, sorry. Somebody needs to get in. Can you admit this person? There's somebody in the waiting room, guys. Can anybody see who needs to be admitted? Ben? Anybody? Is there somebody trying to get in?
I don't see anybody.
See anyone?
Hold on.
There is a guy asking Group A.
What's that?
Oh, never mind.
Did he get in?
You know
His name is Horan Yun, Y-U-A-N. Is he in or not?
I didn't see him, but he should receive the Zoom link from the Group B.
All right.
Yeah,
You're not
saw him.
co-host. In the mode, the screen sharing, I can't see this waiting room thing. Can anybody see the waiting room?
He joined. He's in.
He's in? All
He's
right,
in though, yeah.
Good. Anyway, so we have this. Don't worry about sigma. Something I have to do is always make sure pi is there. This program does not have the automatic pi is pi, so you have to define that. And this is capacitance was 2 times 10 to the minus 12, right? All right, so first they wanted Z naught, so we can get both gamma and Z naught. So Z naught would be equal to the square root of R times, I got to put omega here. R plus 1J times omega times L. Oops. 1J times omega times L times G plus 1J times omega times C. And here, what was G for this one? 1 milli.
Sir?
Yeah, go ahead.
I thought it was divided in the characteristic impedance.
It is. This is gamma, actually. You're right. You're absolutely right. All right. First, Z naught is that, and then I'm going to take the way I'll ask you for your answers. I'll ask you for the magnitude of Z naught and the angle, and that would be in degrees. So, did y'all get that, by the way? You check your answers. Yes.
Yes, sir.
Just the thumbs up. How many got that? I want to make sure I'm talking to a group of people who got. There's no problem. Now, your calculators sometimes have trouble with this. I'm just leveling with you. They do. The next thing we're going to get is after Z naught, we want to get gamma. So I can actually make use of this, I think, and change it. So gamma is equal to, oops, maybe not, R plus 1J times omega times L times G plus 1J times omega times C, and gamma equals that and magnitude of gamma. And really, for gamma, you should just leave it in terms of real and imaginary. So one point I'm going to make, the angle of Z naught is not the angle of gamma, and that's something you should realize just for now. All right, then what did they say? They want the distance at which only 1/3 of the power will be left flowing down the line, correct? So, you know, power in general, when we talk about power, to say how many watts were put into it at all or not. All right, last time I did this, I believe, I showed you the power equation, that power as a function of Z was equal to some P naught times EXP to the -2 times alpha, right? Times Z. Do y'all remember that, class? Give me a thumbs up, some way of indicating that you see it. You got it, everyone? And please turn on your camera. It helps me get an understanding if you see what I see and understand. All right, everybody good on that? Now, in general, the thing that people forget is Z. I can make P naught anything. I'll just make it 1. I'm going to talk about this for a second. Alpha is this. Alpha is simply the real part of gamma, right? And so alpha is 0.331. Are you with me, everyone? Now, if I look at this equation, I know that P of 0 is just 1, because I made it that, right? That's the initial power. And you want to figure out what the power will be, or sorry, how far down the line you have to get 1/3 the power. That means what you're going to do, and here is where I'm going to go to my camera. I hope that this works all right. Now I've got to do one thing. Well, actually, I think you see this. If I say this is 1/3 P naught on this side, the P naughts cancel, and I put 1/3 on this side is equal to EXP to the -2 alpha Z. Do you all agree with that? All right, now I'm just solving for Z. So then if I take the natural log of, in this case, 1/3, right? That's equal to -2 alpha Z. So if I take this and divide it by -2 times alpha, then I should get Z. Do you agree with me? Everybody? All right, is that the answer you got?
That is.
All right, and that means the answer that I posted is not right. And these are from a very old homework set, but let me correct that. So it's actually equal to 1.658. Thank you for letting me know that there was a problem. And that's how to do that one in a nutshell, right? Any other questions about this? And these problems, problems 215, 218, 19, 20, 22, and 23, did anybody have any trouble with that?
I had some trouble on those.
Okay. Which?
15, especially trying to find beta in 2.15. And then a couple more when I was trying to find voltages, like halfway down the line or at the source.
All right. Good. We can talk about those. And there's some things I'm going to be talking about today. I'm going to first, hang on for 1 second. Okay. I didn't put the solutions to these up. I will from now on, if you remind me, because this stuff, Dr. Wentworth Solutions manual is all over the internet. You can probably find it anywhere, but I'll put it up there. This is an interesting one. So they give you a frequency. Let me cast my screen. I need to share a different screen. I need to get my document camera working. Actually, I can share that screen anyway. Come on. All right. All right. This is problem 215, and it has it'll sharpen up in a second, I think. Come on. There we go. 215. And it says that the frequency is 2.4 gigahertz, right? And then it says that is launched on a 1.5 meter length of line, terminated into a matched load. So here's what we got. We got some ZL here and some Z naught here. We know the length of this line is equal to 1.5 meters. And it takes 2.25 milliseconds to reach the load. So that means you got transit time here of 2.25 milliseconds, right? Everybody with me on this? All right, now you know yourself that what we're dealing with is a very fundamental physics problem. We're looking for the velocity on that line. And velocity is always going to be equal to omega over beta, isn't it? Do y'all remember doing this class? How we got phase velocity? All right, it's omega over beta. That's where we took the phase, which is omega t minus beta z, and took a derivative of the phase with respect to time and set it equal to 0. Then we solve for dz dt, and it would be omega over beta, correct, everyone? Now, when we have this phase velocity, how do we get this from this information? Well, phase velocity is really dz dt, and the dz would be 1.5 meters, and the dt would be 2.25 milliseconds. Do you all agree with that? Right? He says it's terminated into a matched load, and a matched load means ZL is equal to Z naught, and the reflection coefficient at the load would be 0. Do you all remember the reflection coefficient, class? Thumbs up or down? Okay, good, good. So that means dz dt, and here's where I jump out of this screen and I go to here. So dz dt for this one or V, I can just call it V phase, or just V, for this one is going to be equal to 1.5 divided by 2.25 times 10 to the minus 3. And that means it's 666. Is that, I'm wondering if that should be microseconds or something like that.
I think it was nanoseconds.
Oh, is it nano? I'm
Nano.
sorry. If it's nanoseconds, that makes a lot more sense. Thank you very much.
I think it's 6.65 or 6.25 nanoseconds.
It's 6.25.
That's it on.
Mine has 2.25. How many have 2.25 nanoseconds for problem 15? 1, 2, and you have 6? Well, most of the class does. What book are you using?
The applied electromagnetics.
This book?
Yep.
Huh?
Yep.
This says, well, let me just show you this because this is a little weird. I'm not used to having Whitworth's book be. This in mine says 2.25.
Yeah, mine says it takes 6.25 nanoseconds.
You must have addition or something like that. I think everybody here except you has 2.25.
That's weird.
But regardless, it doesn't matter. Regardless of how long it takes, this is the way you get velocity. You take the distance traveled divided by the time it takes to travel that distance. Everybody got that, right? So now we know that, I know it's 6.667 times 10 to the 8th. That means V phase is 6.667 times 10 to the 8th meters per second, which makes no sense because that's faster than the speed of light, isn't it? 3 times 10 to the 8th meters per second is the speed of light. So this makes me think that maybe that 6.25 was probably an adjustment Whitworth made in a later edition, because this problem would make no sense. You would have a velocity greater than the speed of light. So what I'm going to do is this. Let's strike that. And let's go with 6.25. Yeah, I like the 6.25. It'll make it realistic. So it's 2.4 times 10 to the 8th, which is less than the speed of light, which I like that a lot better. So that means here, when I'm doing this problem, I have omega over beta is equal to V phase, right? Now we're after beta. Are you with me, everyone? People? Now look, how do we get omega? Anyone? You can turn on your mics. It's fine.
2 pi f.
That's right. From here, you're going to say omega is 2 pi f. And that means beta, right, would simply be equal to omega over V phase. That's 2 pi f divided by the phase velocity. And let me get it for you. I'll give you the answer. I got to put F equals 2.4 gigahertz. Omega equals 2 times pi times F. And then beta is equal to omega divided by V. And that is phase velocity. So that's beta. And now if we wanted to get alpha, how would we get that? I gave you a conversion to get it directly. How would you get alpha, anyone? This is for a problem 2.15. Well, look, you remember if you have alpha, it can be in Napiers per meter, right? Or it can be in what? dB per meter, correct? Y'all with me? Now in dB per meter, I want to be careful that everybody follows me. If it is in dB per meter, then if we have alpha times the distance z, that would be the total attenuation in just dB. All right, we don't have alpha, we're looking for that, but we have the distance traveled. It's 1.5 meters, correct? Everybody with me on this? And we know the attenuation, according to Whitworth's book, it's 1.2 dB. That means alpha would be equal to 1.2 over 1.5, and that would be dB per meter, right? Are you with me, class? And what is that? That's 12 over 15, so that's 3/4, right? Or wait a second. Divide by 3, that's going to be 4/5. So it's 4/5 or 0.8 dB per meter. How do I take dB per meter? This would be dB per meter. Oops, you can't see that. Sorry about that. I got to get this back up. Here's what I'm doing. I'm actually saying I had alpha in terms of blank Napiers per meter, which would be so many dB per meter when we do a conversion. And do you remember that 8.686 alpha, and this would be in Napiers per meter, equaled blank dB per meter? Do you all remember that, class? All right, so we've got dB per meter, we want alpha and Napiers per meter. We have to divide this 0.8 by 8.686. So alpha is 0.8 divided by 8.686. And what is that going to end up being? Oops, it's 0.8 over that. .092. All right. So that means the propagation constant would be equal to alpha, and I'll put it here. This would be the symbol for propagation constant is alpha plus j beta, and alpha is 0.092 plus j, and beta was, I didn't write it down here. Can somebody tell me what beta was? Anyone? We calculated it, right?
62.8.
All right. And that should be the propagation constant if you'd use the correct value for, or if you use the time of 6.25 nanoseconds. And I'm glad somebody saw this discrepancy, because 2.25 is not something that's going to make sense. Everybody got that? Some of you are going to ask questions about this or have questions. Is that sort of a representative problem? Yes, it is. It's something where you literally have to do reverse engineering. You have to take the knowns and figure out the unknowns. And you have the equations that dictate behavior. Now, do you all understand this problem? It should be fairly straightforward, right? Everyone? Okay. Other questions? Ben, did you have some more?
Could you do the last one, 2.23?
Can't hear you, Ben.
Could you do 2.23, the last problem?
2.23? Oh, this is the complete circuit. Okay. how far did I get last time? I was doing the complete circuit, wasn't I? I started with the input impedance. Let me take you through a little part of the lecture. This is perfect. And I want to tell you one other thing about the way I've learned to lecture on Zoom, these remote. What I do is give you a reading assignment, and you should have seen the reading assignment. Where is that? If you look at the actual homework, it says read pages 62 to 73. Something I learned, this link is dead now. I don't know if you've noticed that, but that link doesn't exist. I'm sorry about that. But in pages 62 through 73, it discusses a lot of the stuff we're going to talk about. Now, if you can get a fresh sheet of paper here, because this is going to be some important stuff, and I want to take you through what's called the complete circuit. I didn't get there last time, did I? No, but I got to the, what I did was this. I said for a lossless line, what we end up doing is finding the input impedance Z in at a given length L was equal to some Z naught times ZL plus JZ naught times the tangent of beta L over Z naught plus JZL tangent of beta L. You all remember that, right? I worked that. Do you remember seeing this equation, class?
Could you scoot the paper over just a little bit, Professor?
Oh, yeah. I'm sorry. Just thumbs up if you remember seeing it. Give me some inclination. All right, good. Everybody has seen it, and they should have. Now, beta is again the wave number. And here we're assuming it's lossless or low loss at least. Now, if we have this for a transmission line, this is the complete circuit. This is important. And I want you to take, I'm going to go through this slowly. Usually you're familiar with having a voltage source of some type. And the voltage source is usually something like 20 cosine of omega t plus some phase angle volts. You remember seeing that, right? That's in the time domain. We don't use the time domain if we don't have to. Our representation of this voltage would just be 20 at an angle of theta. And I could have put V naught here. I put 20, honestly, because I want you to think in terms of real quantities, not abstract quantities. Are you with me, class? You remember you would see a circuits problem 20 at an angle of 30 degrees. Everybody remember that? It implied that the frequency was constant and it was a cosinusoidal variation. So regardless what this is, if this is going to be some voltage here, some V at an angle, V naught at an angle theta. Now there's going to be some impedance, and I call this Z, you can call it Z source. There's an impedance associated with the voltage source that you can't get rid of. You can call it anything you want. It's some impedance there. Then there's your transmission line. Usually when they do transmission lines, they'll show you things that are actually thin little cylinders that show the cabling. And then they'll have a load, Z load here. Now, this transmission, does everybody understand this is the symbol for the transmission line, class? Usually, they'll put the characteristic impedance right in there. They'll have Z naught equals something. And the length of this line will be L. Now, when we're solving a problem like this, what we need to do is get the voltage just inside, just on the other side of this transmission line connection. We call that V prime. We're going to get that in a second. Remember, when this is connected to this source, the source really just sees an impedance right there, right? That's all it sees. And what impedance does it see? It sees this impedance right there. So right at this point, it's seeing Zn of L. Can everybody understand that? If you were to measure the impedance, right here, you would measure this quantity. Everybody with me, class? So the first step is to get V prime. It's how much voltage is just on the inside of that transmission line. And the way we get it is this. We're going to take our voltage source. That's just the volt. I'm putting some angle. You put your ZS here. And then you replace this with just Zn, the input impedance of the line. And the voltage developed across Zn of L is the voltage V prime that we're after. So what would V prime be, anyone? It's a simple voltage division problem, isn't it? Class? That's two series impedances, right? So V prime would be what? V naught at an angle, whatever the angle is. And then it would be simply Z in, I'll remove the L, over Z in plus ZS. Y'all agree with me? You can give me a thumbs up or some indication that you do. You can shake your head, whatever. Everybody got it? All right. What is this V prime really, though? And here's something I'm going to say. I've got to say it again, too. When we're talking about these transmission lines, come on, we always go ahead and we make the load at Z equals 0. And this is going to be positive Z on this side. So that this point right here is actually Z equals minus L. Now, I want you to make sure you understand that. The way Wentworth's book is set up and all the equations that we're going to talk about relate to a coordinate system where the load is at Z equals 0 and the transmission line itself extends from 0 in a negative direction. Okay? Now, because of that, this V prime, remember the voltage anywhere on a transmission line, and when I say the voltage, some V of Z is the voltage at any point Z between the, I call it the upper and lower conductor, right? It's a differential voltage. That voltage will be equal to some V0 plus, and we're going to do this for the lossless case, and it would be e to the minus j beta Z, and then it would be plus the reflection coefficient at the load times e to the j beta Z, and the reflection coefficient by definition. Oh, by the way, Ben, are you recording this?
Yes, I am.
Thank you. And did anybody have any trouble viewing, if you looked at the previous lecture on the Zoom, on the link that Bill gave? Could everybody, or Ben gave, can everybody see that? Did anybody look at that? Let me ask you that, because I didn't. Nobody? Oh, you looked at it? You did, Andrew? Okay. And you could view everything fine? Oh, okay, good. Well, what is the reflection coefficient, by the way, at the load on a transmission? Do you remember?
ZL minus Z naught over ZL plus Z naught.
Yeah, and the way I always remember it, it's always the impedance you're going into is what you get first. So that would be ZL, because the waves are coming from the source, minus the characteristic impedance of the line over the sum of the two, ZL plus Z naught. That's always going to be the reflection coefficient. And in general, that's complex. A magnitude at an angle. Now, this is the equation on the line, right? That's the voltage anywhere on the line. And we've got the reflection coefficient if we know ZL, correct, class? I'm doing it in general. We have the reflection coefficient if we know ZL and Z naught. And if we know the length of the line, now this is what we're after. We're after V0 plus. So when I take a look at this V of Z, that's the voltage anywhere on the line. I have calculated the voltage right here, just at the point where this voltage source transmits a voltage waveform onto the transmission line. It's right at the edge of it. So now what I can do is say this, well, I know that V of Z equals minus L is actually equal to my V prime, right? And I'll put it down here. is V prime that I've calculated earlier, and that's got to be equal to V0 plus e to the, now it was, before it was minus j beta z, but because z is minus L, this becomes plus L, plus the reflection coefficient at the load times e to the, normally it's plus j beta z, but because z is minus L, it would be minus j beta L. Can everybody follow me on that? Everybody understand what I've done here? The V prime was what we calculated through voltage division right here. And it is equal to this. Y'all see it? Okay. Now I'm after V0 prime. So I can say that V0 plus, or V0 plus, pardon me, is equal to my V prime, there's V prime, over e to the j beta L plus gamma L e to the minus j beta L. Does everybody agree with that? Now V0 plus is really the magnitude of the wave that's going in the positive direction, but superimposed on that is the wave traveling in the negative direction. That's this portion right here. And so these two are complex and they make up the phasor form of the voltage at any point in the line. And that's V0 plus, all right? That's what we're after. Box that. Now, once we have V0 plus, if they want the voltage at the load or anywhere on the line for that matter, then I can say, regardless of where they want it, I can say that now V of Z is equal to my V0 plus times e to the minus j beta z plus the reflection coefficient, right, times e to the j beta z. And that would be the voltage anywhere on the line. Where you usually want the voltage is at the load. That's typical. So the voltage at the load, well, what is z at the load, class? Anyone? What's the coordinate z at the load?
0.
0? Y'all agree with that? We made it 0, so our calculations would be easy. That means when z is 0, it's just V0 plus. And what is e to the 0, anyone?
1.
1, right, 1. So it's 1 plus just gamma L, right? And that is the voltage at the load. Can you follow me so far? Give me a thumbs up, thumbs down if you understand what we've done. With me? Okay. Any questions? This follows in a logical order and it's in Wentworth's book and it's discussed. Has everybody got that? Now, that's the voltage at the load, right? You can call it just VL. Now, if that's the voltage at the load, what would the current at the load be? Just tell me. How do you get current if you got voltage?
Divide by the load impedance.
That's right. If we take V load divided by Z load, now I have current, right? Okay. And if I want power, how do you get power? Well, isn't power equal to average power? 1/2 the real part of V times I conjugated. Remember? That's power, isn't it, class? In the phasor domain, 1/2 the real part of voltage times I conjugate. That means power is 1/2 the real part of the voltage, V of L, right, times this conjugated. Well, if I conjugate that, I get VL conjugated divided by ZL. Can you all see that right there? I'm just taking VL times I conjugate. Well, I is VL over ZL. When I conjugate it, I conjugate top and bottom. So I get VL conjugate over ZL conjugate. It should be ZL conjugate, sorry, right? Everybody with that? Okay with that? And I have to go to the next piece of paper. Now, VL times VL conjugate is just equal to VL magnitude squared. Let me explain that. If I have VL, and I'm just going to show you this. If I, let's say VL equals to A at an angle theta, what is VL conjugated? Anyone? What happens when you conjugate something?
You make the angle negative.
That's it. That's the only thing. A at an angle of minus theta, right? Now, what happens when I have VL times VL conjugate? That would be A at an angle of theta times A at an angle of minus theta, or simply magnitude of A squared. Correct, class? The angle goes away. Are you with me? Please be attentive to this part. That means for power, my average power at the load, this is at the load, it would be equal to 1/2 the real part of, and now it's going to be the magnitude of VL squared divided by Z, right? Conjugated. So it's really the magnitude of Z load at an angle, but if it's conjugated, the angle becomes minus the angle of the load impedance. With me so far? I want you to make sure everybody just write that thing down, and then I want your eyes up here when I talk about the next part. Now, look, VL squared is all real. It's like 100, 1,000. There is no plus J. So I can say that this P average now is equal to 1/2. I can take the VL squared out in front, all right? And now I've got the magnitude of ZL here I can take out in front. And now I have the real part of this angle. Well, if I have e to the minus j angle associated with the load impedance here, when it comes upstairs, it's really e to the j angle of the load. You know, when you write an angle, you can put like an angle of 20, or I mean, an angle of say 45 degrees, or that's really equal to e to the j 45 degrees, or e to the j pi over 4, right? All those are representations of the same thing, right? So when I put angle down, I could put the symbol angle at theta L, or just e to the j theta L, right? Y'all with me on this, class? Thumbs up or some way of indicating it? Head bob, anything. All right, what's the real part of that? And what do I use to get it? Anyone?
Cosine theta L.
Yeah, what you're going to do is take e to the j theta L and expand it as cosine theta L plus j sine theta L, correct? And then you take the real part, which is the cosine. So the bottom line is the power, average power at the load is simply equal to 1/2, all right, times magnitude of VL squared over magnitude of ZL square, or magnitude of ZL, not squared, times the cosine of theta load. And that's it. And now you've got the complete circuit. Is everybody okay with that? I'm going to get back to problem 23 now, because this should, what I've just shown you should answer any questions you have. So in problem 23 in the book, it says, referring to figure 213, consider a 75 ohm lossless T line. So let me find figure 213. Right here, I've got an input impedance. I've got the load at, come on. I've got a load at 0, and I don't know why it does that. And oh, in Whitworth's book, by the way, he used the lossy form of the voltage on the transmission line. It's almost never used. I'm just telling you that. He used it. See how he has a gamma there instead of J beta? So he has e to the, he has e to the positive alpha L there, that means he assumed it could have a loss. It could have an alpha that's not 0. Almost all the time, we don't do that. But he's talking about this. So when I come over to 223 in the book, and you can look at it on your own, it says, referring to figure 2.13, consider a loss of 75 ohm line. So I'm going to do this problem. So first thing I have is Z naught is equal to 75 ohms. With phase velocity, next he gives you V phase is equal to 0.8 C. And it's 30 centimeters long. So the length of the line is 0.3 meters. The supply voltage is 2 cosine of omega t. So when I'm drawing this circuit, I'm not going to put 2 cosine of omega t. What I'm going to do is this, plus simply 2 at an angle of 0 degrees volts. He gave it to you as cosine of omega t, but we work in the phasor domain. And then he has the ZS is 75 ohms, so he has a 75 ohm resistor here. And here's his transmission line. And this has a Z naught equal to 75 ohms. And then he has a load here. And Z load is equal to 100 plus J 125. And the frequency is 600 megahertz. (600 times 10 to the 8th). And the first thing is they want a Zn. Now class, I'm going to ask you to try to calculate this with me because you're going to see, you're going to have mistakes in your calculator. This happens in every class I've ever taught because proper operation of the calculator is a problem. I'm going to use MathCAD to calculate. By the way, I'd encourage you to get a copy of, downloaded the copy of MathCAD and contact Network Services. Let me just put the number here. It's going to be in your homework. It's 844. What is it? I think it's for 2280 is Network Services. And I put that in your homework in the last homework. So you can call them if you want to, once you download it, if you want to get a license like I have, so you can have the full use of it. Without the license, it won't do some things, like it will not give you the angle and stuff, but MathCAD I love. And you can see the screen I have here, right? Oh, sorry, you're looking at the MathCAD screen, right? Aren't you? Right here. All right. Well, let me tell you, I'm going to go back to that in a second, but the first thing we had to do is calculate the characteristic impedance, right? So what I'm going to do is, what I always do is just go up here and modify stuff. First, the frequency was 6 times 10 to the 8th. So it's going to be 6 times 10 to the 8th. The next thing is he gave me Z naught as 75, right? And then he gave me ZL as 100 plus 1J times 125. He gave me the phase velocity as 0.8 times C. Make sure C is 3 times 10 to the 8. That is. And then I can get rid of all this stuff. And this stuff. And first thing I have to do is get Z in as a function of L. And I'll make L equal to, is linked on that? .30 centimeters, so it's 0.3.
Professor,
Yeah,
what happens if you accidentally define one of these variables twice, like you forgot to delete a previous definition and
the last thing it's defined as will be used. Like if there's L up here is 6 and then L below it is 0.3, 0.3 will be used. It's just like in a computer writing programs in C or something. It's always the last defined value is the one that's in memory.
Okay.
So for this one, we've got to get beta for this one, right? So we got 0.8c, and we know that velocity is omega over beta, correct? Everybody? So velocity is omega over beta, and we want beta. Then omega over velocity would be beta, correct? So beta would be omega divided by phase velocity. And I didn't put omega here, but I'm about to. My omega is 2 times pi times f. And that means my beta, you can check yourself on that, is equal to this. Correct, class? I'm just using the fundamental definitions. And that means now I can go directly to this equation, because that's what I want. And matter of fact, I can make this a function of z so I can get the impedance anywhere. And I'll say it's equal to some z naught that I've defined times, and then it's ZL, right? Or Z capital L, plus 1J times Z naught times the tangent of beta times Z. I'm going to put the Z in. No, I better put L. I just thought about that. I better put this as L, because L is strict positive. So I got this. And then I have to divide that by Z naught, right? Plus 1J times ZL times tangent of beta times L, or sorry, L. And y'all can see that, right? So my Z in of L, sorry, capital Z in, is that, or its magnitude is this, and the argument or angle of Z in of L is that. Now, you have calculators. How many got that for magnitude and angle or real and imaginary part for ZL? Go ahead and try it. You're going to see you're going to make lots of mistakes. A lot of it has to do with the arguments of the tan function. That should be in radians. How many have like TI 93s? Anybody? 89s? 1, 2, 3. What are the other ones you got? You've got, there's something, is it called Spire? Or what's the one, the latest TI calculator? What is it called?
I got 84 plus.
An 84 plus will do it. But
It's
there's
the TI Inspire.
Inspire, yeah. And that's the latest, isn't it? So go ahead and run that calculation just to prove it to yourself. And I bet you're going to see you get some wrong numbers. What I tell people to do is use the calculator memory sorry about, I'm getting email and they just show up there. That's a professor from long ago. You got it? You got it right, Tyler? Okay. Anybody else? I'm giving you a second to try this. How many got the wrong answer? Let me ask you that. Anybody?
I got it a couple times wrong on the homework and I had to check myself and realized I did it wrong.
Telling you this much, those calculators are wonderful pieces of machinery in a sense, but if you don't use them right, they won't work. And the worst thing is you're going to get weird things when you have the J in front of the Z naught. Really, the way to put that in there is probably e to the J pi over 2 or 1 at an angle of 90 degrees for J. But really, with Inspire, I don't know if they have a different way of doing real and match. Anybody else? All right. I'm going to move on from there, but just trust me on this one. This is the calculation people bomb on, and then it ruins the rest of the problem. If you don't get this right, nothing's right. So if we have that, the next thing I have is I've got to get the input voltage, right? I've got to get that V prime. Are you all with me, class? Right? That's the voltage just on the inside of the transmission line. So if I want V prime, the way I go get it, I'll call it V prime. That's equal to what? My V naught, right? V naught or V source times, and then it's going to be Z in. Matter of fact, what I'm going to do is this. I'm going to call just Z in, small z in equal to Z in of L, so I don't have to keep retyping all this stuff. So it's going to be Z in, small z in. All right, let me shut this email off. Z in over Z in plus Z naught. Come on. And my V naught on this one he doesn't give us that. Or does he? Oh yeah, he does. It's 2. So V naught is just 2. All right, that means my V prime, and I'll just take a magnitude. So V prime is that, and that means magnitude of V prime is this, and the argument of V prime is that degrees is going to be minus 35 degrees. Now I need to get my V0 plus, right? I'll call it V0P. And how do I get that? Y'all remember? It's worth me talking about this. Remember when we were doing this, when we were doing these problems, I said that V0 prime was right here, right? We just calculated V0 prime. Now we need to get this we need to get V0 plus. So we take V0 prime, that would be when Z is equal to minus L, and divide it by e to the minus j beta z, but z will be minus L, so it would be e to the j beta L plus the reflection coefficient times e to the minus j beta L. And I'm going to do this. I didn't get the reflection coefficient yet, did I? So I need to get the reflection coefficient. I'm just going to call it gamma L right here. And the reflection coefficient is equal to what? Well, it's ZL minus Z naught, that quantity divided by ZL plus Z naught. And that means the reflection coefficient as a magnitude of that, and the argument is in degrees, right? I'm not going to spend time doing WYSIWYG with Greek letters, so I'm just using a capital TL as gamma L. Okay, class? And that means this is the definition of the reflection coefficient. The magnitude of it should be 0.593, and the argument should be 43.125 degrees. You all get that, don't you? Now, I need that because I want to get V0 plus, and I'll remind you, I'm going to take this down. Oh, sorry, let me leave it up. That my V0 plus that I'm after right here is going to be equal to V prime that I just calculated divided by this term. So I had to get the reflection coefficient to get V0 plus. Correct, class? All right, now let me go back here. So that means this is going to be V prime divided by, and now I take EXP, and it's going to be 1J times beta times L, and my L is 0.3, plus the reflection coefficient, right, times EXP to the minus 1J times beta times L. And that means my V0 plus is equal to that, or it looks like it's just J1. The magnitude of V0 plus is 1, and the argument of V0 plus is 90 degrees. So it's 1 at an angle of 90 degrees. Can you all verify that, class? Now, I know this gets a little confusing, but can I get a show of at least thumbs or head nods that you understand it up to this point, what we're doing? We're using the source voltage to get the voltage on the transmission line at the beginning of the transmission line using voltage division. And we calculate the input impedance. Then we use that voltage to get V0 plus. And from there, the last part, we need the voltage at the load. So how do we get the voltage at the load, people? Let me get rid of this. Anyone? I'm going to call it just I'll call it VL. Voltage at the load would be what? Anybody remember?
V0 plus times 1 plus the reflection coefficient.
Right, V0 plus times, and now the e to the j beta z becomes 1 because z is 0, it's at the load. So it's 1 plus the reflection coefficient. I have a comment about this, by the way. Now, you'll notice that VL here has a real and imaginary part, right? This is a typical mistake. People will ignore the imaginary. They'll just look at the real for some reason. I think it's the way your calculators render it. At least this is my thoughts on why it happens. And they'll make a lot of wrong assumptions. Really, you always want to do this in polar form. So the magnitude of V load is equal to 1.49 And the argument of V load here is going to be 105 degrees. See if you guys can get that. Yay, nay, anything? You got it, Tyler? Anybody else get this? All right, that's the voltage at the load, right? And if we wanted the voltage at the sending end, that's just V prime. Now I'm going to talk to you about another. Are you good for me to give a little more of a lecture here? Okay. With me, class? All right. I'm going to talk about something. Now, when we take a look at this equation, V of Z is equal to, sorry, V of Z is equal to V0 plus times e to the minus j beta Z plus the reflection coefficient times e to the plus j beta Z. If we were to graph that versus Z, suppose the loads here is equal 0, and we took a look at just V of Z, a magnitude of V of Z, what we'd see is this. We'd see something that goes like this until finally at the load would have a value. Are you with me? This would be, if you graph this thing and took the magnitude of it and versus Z, this would be Z equals minus L. You would see something that undulates or changes periodically in a very predictable manner. Now, here's the important things I want to stress. The peak value would be here and the minimum value would be here. Do you all see this? I'm just showing you what this thing would look like. But the maximum, V max, on the transmission line in a phasor form would be V0 times 1 plus the magnitude of gamma L. That should be kind of intuitive to you because e to the minus j beta Z is something that's just got one at an angle of something, right? So if you have one at an angle of something, and this is one at an angle of something on S minus the angle of something, there's going to come a point when these two things superimpose from maximum value. And it happens to be this value, 1 plus gamma L times V0 plus. Now V minimum, the minimum value it would have would be V0 times 1 minus the magnitude of gamma L. All right, that's the minimum value. What we like to do when we talk about transmission lines is take a look at the ratio of the maximum to the minimum. It's called the standing wave ratio. And the standing wave ratio, a lot of times it's voltage standing wave ratio, they're the same thing. They'll put VSWR, but the voltage or just the standing wave ratio is always going to be 1 plus gamma L, and that's got a magnitude over 1 minus gamma L. Now, I want to talk for a minute about this. I know I'm about 1 minute over right now. This is my office hour time. Does anybody have a problem with me going on for a few more minutes about this? You need to go? Okay, I assume you don't, but I want to finish up this thought because it's a good one. It's important. Now, if we look at the VSWR of that, right, it's 1 plus gamma L over 1 minus gamma L. When you have a matched load.
Yes, sir.
Yeah.
Can you scoot the paper over or the
Yeah.
camera?
Can you see it? Can you see that paper or not?
Oh, we can see half of it.
Oh, okay, all right.
Thank
Matched, matched load. The matched load is when ZL is equal to Z naught. And the reason it's called a matched load is there are no reflections. Obviously, if you think about the reflection coefficient being equal to ZL minus Z naught over ZL plus Z naught, that will be 0 when it's a matched load. So the matched load means ZL, or the reflection coefficient, is 0. Now, something else. When you have a matched load, what is the voltage standing wave ratio, or the standing wave ratio? Just take a look. If the reflection coefficient is 0, what will this value be? Anyone? Go ahead.
1.
It's just 1. That's it. Now, if you have a short circuit, so there's the first one, a matched load. If you have a short circuit for your load, well, what's the impedance of a short circuit, anyone? If you say you got a short circuit, what's R? How much resistance in a short circuit? Anyone?
Infinite.
Short circuit.
0.
0, right? That means ZL is equal to 0. What would the reflection coefficient be if you have a short circuit? Take a look. It would be what? Reflection coefficient would be 0 minus Z naught over 0 plus Z naught, or minus 1. Do you agree with that, everyone? All right, that's if it's a short circuit. So what happens to the voltage standing wave ratio in that case? People? Well, just take a look at the equation. If that's the voltage standing wave ratio, 1 plus gamma L, magnitude of gamma L, over 1 minus gamma L. If I have 1 plus 1, I have 2, right? And if I have 1 minus 1, I have 0. What is 2 over 0 in a word? Anyone?
Infinity.
It's infinite. That's my point. The voltage standing wave ratio is infinite. That means on this little diagram, it would go to an absolute 0, and then it would come, the thing would do like this. And you would get the ratio of peak to minimum is infinite. Now that's a short circuit. What happens if we have an open circuit? In other words, at the end of the transmission line, if we just have this and we don't attach anything, an open circuit has a load impedance of what? You're familiar with the term open and short circuit, aren't you, class? All right, an open circuit has an impedance of what, mathematically?
Infinite.
Infinite, right. So that would be an infinite impedance. So what would the, first, what would the reflection coefficient be if it has an infinite impedance, or an impedance tending to infinity? Well, look at the equation. This is reflection coefficient, right? So if I have something tending to infinity minus Z naught, it's about something to infinity. And something tending to infinity plus Z naught, it's really 1, isn't it? Class? Y'all see that? Now, if the reflection coefficient is 1, what is the voltage standing wave ratio? Go back to this equation. If gamma L, remember we only care about the magnitude of gamma L. If gamma L is 1, what is the VSWR?
Infinity.
Infinity. That's my point. So what'll happen is, no matter what the load is, the limits for the values of the VSWR are from 1, which is what you would like to get. That's what you want, to infinity. Are you with me, class? It's never below 1. And what the mistake people make is they forgot the magnitude here. And they'll make this a complex number. It's not. You have to take the magnitude. It's not the real part. It's the magnitude of the reflection coefficient. Got me on that, class? And that's the VSWR, and we use that a lot. Now, today, I didn't get time to do this, but I'm just going to mention this and I'm going to give you some reading. And really, we're through up to the Smith chart point, as far as I'm concerned. Now, this Friday, I'm going to have a short quiz based on the stuff that we've covered, all right? And then it'll be something where I email you the quiz at the beginning of class. I used to do it at the end, but I'm going to give it to you at the very beginning of class. And you'll get 20 minutes to do it, and then you have to upload it to Canvas, and then we'll start our regular lecture. Is that all right with everyone? And it's going to be something, it will be open book, open notes, but I'm going to ask you to turn your cameras on for this one. I'm trying to tell you, I'm going to have to trust you at some point to stay off the internet. Obviously, if you get on the internet, you can do stuff, and you can do it with your phone. You're going to have to take pictures with your phone, put it back on Canvas. So I email you it, all right? Matter of fact, no, I think I'll do it this way. If you have a scanner, fine. I'll email you the quiz. You show me your work on the quiz. You do it. You can print it out or just write down the problem. Then take a picture with your phone. You've probably had to do this before, right? How many have done this where you had to take a picture of something and put it on Canvas? Haven't y'all? All right, you take a picture, but I want it in a Word document. Don't give me a PDF, put it in a Word document. It makes it easy for me to edit. Put your solutions in a Word document. Make sure you put your name on it in quiz 1, something to indicate which quiz it is, and then upload it to Canvas. And what I end up doing is I grade them with a tablet I have here, a Lenovo. It's actually a Yoga what is this? A ThinkPad, but I can grade it using a stylus there, and then I can send that back to you. Basically, what you're going to get is a graded quiz, and you'll be able to use that and reference it. And the nice thing, it's electronic, so you can't lose it. So you just keep piling them up in Dropbox or something like that. Fair enough on that? Yes.
You said you want a PDF or you don't want PDF?
No, I do not want a PDF. I want a Word document, W-O-R-D. And so when you take pictures from your camera, first make sure you use a black pen and either yellow or white paper. It has to be high contrast. And second, put it in a Word document. Now I'll send this information out too at the quiz. It's not going to be a difficult one, but it's something that you're going to have to be up to date with everything and know how to use the actual equations efficiently. The other thing I'm going to tell you is where we're going is the Smith chart, and this becomes so important. And in the development of the book, you're going to get a little blown away by the mathematics, but I'm just going to mention this because I'm going to ask you to read this. In his book, what he does is indicate this is a Smith chart, and it's what I've uploaded. And then he goes through the equations, how they took the reflection coefficient and manipulated it and basically got equations for circles. And the center of the circles have to do with the real and imaginary part. Now, I'm going to let you read this at your leisure, but remember the equation for a circle is always what? X squared plus y squared equals radius squared. Y'all remember that? And then if the center is offset, it's going to be x minus x naught squared plus y minus y naught squared is equal to the radius squared. That's these equations here, 292 and 293. I don't have time to go through it today. But what happens when you do that, when you graph the real and imaginary part to trajectories on the Smith chart, it allows you to literally find, and I'll have to show this next time, the impedance or the reflection coefficient at any point on the transmission line. And you can do things, the reason this is so beneficial, you can do impedance matching with this. We'll take this up next time. Listen, do you have any more questions? This is my office hour, so please, you don't have to go, but any questions at all about the homework or what we covered today? You want me to give you a problem?